Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the depths of winter, 1942, beneath the abandoned football stadium at the University of Chicago, history quietly unfolded. Enrico Fermi, the brilliant Italian physicist, stood before a peculiar structure that would forever change humanity's relationship with atomic energy. Chicago Pile 1, as it came to be known, was humanity's first controlled nuclear reactor, a carefully arranged stack of graphite blocks and uranium that achieved the first sustained nuclear chain reaction on December 2, 1942. The reactor itself was deceptively simple in appearance. 400 tons of graphite blocks formed a lattice interspersed with 6 tons of uranium metal and 40 tons of uranium oxide. No concrete containment vessel, no massive cooling towers, just raw physics made manifest through meticulous engineering. When Fermi's team withdrew the final control rod that winter afternoon, neutrons began their dance of fission, releasing energy that had been locked within atomic nuclei since the formation of our solar system 4.5 billion years ago. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. But what if we could take Fermi's revolutionary concept and place it somewhere far more challenging and potentially more valuable than a university basement? What if we built a nuclear reactor on the moon? This isn't science fiction. It's a serious engineering proposition that NASA and other space agencies are actively investigating. The concept combines the fundamental physics that Fermi pioneered with the unique advantages and challenges of our nearest celestial neighbor. The moon presents both extraordinary opportunities and formidable obstacles for nuclear power generation. Unlike Earth, the moon lacks an atmosphere, which eliminates concerns about radioactive atmospheric contamination but creates new challenges for heat dissipation. The lunar surface experiences temperature swings from 127 degrees Celsius during the 14-day lunar day to minus 173 degrees Celsius during the equally long lunar night. These extreme conditions would push any terrestrial reactor design to its absolute limits. Consider the fundamental physics involved. Nuclear fission occurs when a heavy nucleus, typically uranium-235 or plutonium-239, absorbs a neutron and splits into 2 lighter nuclei, releasing enormous amounts of energy, roughly 200 million electron volts per fission event. This process is the same whether it occurs in Chicago or on the lunar surface, but the engineering challenges of containing and controlling this reaction in the moon's unique environment are profound. The absence of readily available water on the moon eliminates the possibility of traditional pressurized water reactor designs that have dominated terrestrial nuclear power for decades. Instead, lunar reactors would likely employ gas cooling systems using helium or other inert gases, or potentially even direct radiative cooling to the vacuum of space. These design constraints force engineers to reimagine every aspect of nuclear reactor technology. The moon's reduced gravity, approximately 1/6 that of Earth, affects everything from convective heat transfer patterns to structural engineering requirements. Components that would be impossibly heavy to launch from Earth become manageable in the lunar environment, potentially allowing for more robust shielding and larger reactor vessels than would be practical for Earth-based applications. Transportation costs remain the primary economic barrier. Current launch cost to low Earth orbit approximate $10,000 per kilogram, and reaching the moon costs significantly more. A complete nuclear reactor system, including fuel, shielding, and power conversion equipment, could easily mass several tons, representing hundreds of millions of dollars in launch costs alone. However, the potential returns, unlimited clean energy for lunar bases, asteroid mining operations, and deep space missions, could justify this enormous initial investment, opening entirely new chapters in human space exploration and scientific discovery. The moon's surface presents a radiation environment fundamentally different from Earth's protective magnetosphere and atmosphere. Cosmic rays, solar wind particles, and occasional solar flares bombard the lunar surface with high-energy radiation that would be largely absorbed or deflected before reaching Earth's surface. This harsh radiation environment creates both challenges and unexpected advantages for nuclear reactor operations. Galactic cosmic rays carry energies ranging from millions to billions of electron volts, far exceeding the energy scales typical in nuclear reactors. These high-energy particles can induce nuclear reactions in reactor materials, potentially creating radioactive isotopes and gradually degrading structural components through radiation damage. However, the existing high radiation environment means that a properly shielded nuclear reactor would not significantly increase the ambient radiation levels that lunar equipment must already withstand. The Moon's lack of magnetic field eliminates one potential complication that affects terrestrial reactors: electromagnetic interference from geomagnetic storms. Solar particle events, which can disrupt satellite electronics and power grids on Earth, would primarily affect the reactor's external systems rather than the nuclear process itself. The reactor's massive shielding would provide protection for sensitive electronics housed within the reactor complex. Temperature management represents perhaps the most significant engineering challenge for lunar nuclear reactors. The 14-day lunar day brings surface temperatures that can reach 127 degrees Celsius, while the equally long lunar night plunges temperatures to minus 173 degrees Celsius. These extreme temperature swings create thermal stress cycles that could fatigue reactor materials over time. Traditional nuclear reactors rely heavily on water for cooling, neutron moderation, and steam generation for electricity production. The Moon's lack of readily available water necessitates entirely different approaches to reactor cooling. Liquid helium cooling systems, while technically feasible, present significant challenges in the lunar environment. Helium's low boiling point of minus 269 degrees Celsius means it would remain liquid even during the coldest lunar nights, but any system breach could result in rapid helium loss to the vacuum of space. Alternative cooling approaches might employ liquid metals such as sodium or lithium, which have been successfully used in experimental terrestrial reactors. Sodium-cooled reactors operate at higher temperatures than water-cooled systems, potentially improving thermal efficiency. However, sodium becomes solid at 98 degrees Celsius, requiring heating systems to maintain coolant flow during the lunar night. The vacuum of space surrounding the Moon offers unique possibilities for heat rejection. Radiative cooling. Panels could dissipate waste heat directly to space without requiring coolant circulation systems. However, the efficiency of radiative cooling depends on the fourth power of temperature difference, meaning that maintaining adequate cooling during the hot lunar day would require enormous radiator surfaces. Material selection becomes critical under these extreme conditions. Reactor pressure vessels must withstand not only the internal pressures and temperatures of nuclear operation, but also the thermal cycling imposed by lunar day-night cycles. Advanced materials like carbon-carbon composites or refractory metal alloys might offer superior performance compared to the steel and zirconium alloys used in terrestrial reactors. The Moon's reduced gravity affects fluid dynamics within the reactor core. Convective heat transfer, which plays a crucial role in many reactor designs, operates differently under lunar gravity conditions. Natural circulation patterns that drive cooling in some terrestrial reactor designs might be insufficient on the Moon, requiring active pumping systems for coolant circulation. Neutron physics remains largely unchanged in the lunar environment, but the absence of atmospheric absorption means that neutron radiation extends much further from the reactor than on Earth. This expanded radiation zone requires careful consideration in base planning and reactor siting. Conversely, the hard vacuum eliminates concerns about atmospheric contamination from radioactive gases that might escape containment systems. Fuel considerations also differ significantly. While uranium remains the most likely fissile material, the difficulties of transporting fresh fuel from Earth suggest that lunar reactors should be designed for extended operation between refueling cycles, possibly decades, rather than the typical 18 to 24-month cycles common in terrestrial power reactors. NASA's Fission Surface Power Program represents the most serious effort yet undertaken to develop nuclear reactors, specifically for lunar deployment. Their baseline design centers on a compact, highly efficient reactor system capable of generating 10 kilowatts of electrical power, enough to support a small lunar outpost or research station. This power level might seem modest compared to terrestrial nuclear plants that generate hundreds of megawatts, but it represents a revolutionary capability for sustained lunar operations. The leading design concept employs uranium dioxide fuel, pellets enriched to approximately 19.75% uranium-235, contained within a compact reactor core measuring less than 1 meter in diameter. This high enrichment level, far exceeding the 3 to 5% typical in commercial power reactors, enables a much smaller, lighter reactor core while maintaining adequate neutron multiplication for sustained operation. Heat pipe technology emerges as the most promising solution for lunar reactor cooling. Heat pipes are sealed tubes containing a working fluid that transfers heat through evaporation and condensation cycles. In the reactor core, heat pipes absorb thermal energy from nuclear fission, causing the working fluid to vaporize and carry heat away from the fuel assemblies. The vapor then condenses in cooler sections of the heat pipe, releasing heat to radiative cooling panels. Sodium heat pipes appear particularly well suited for lunar reactor applications. Sodium remains liquid across a wide temperature range, from 98 degrees Celsius to 883 degrees Celsius, providing excellent thermal transport properties. The heat pipes can transfer kilowatts of thermal power with minimal temperature differences between hot and cold ends, crucial for maintaining reactor temperatures within safe operating limits. The reactor's neutron reflection system requires careful optimization for space deployment. Traditional reactors use water or graphite as neutron reflectors to reduce neutron leakage and improve fuel utilization. Lunar reactors might employ beryllium oxide reflectors, which provide excellent neutron reflection properties, while maintaining structural integrity under extreme temperature cycling. Beryllium oxide's high melting point of 155 degrees Celsius ensures stability even during reactor transients. Control rod systems must function reliably after months or years in the lunar environment without maintenance. Conventional control rods use neutron-absorbing materials like boron carbide or hafnium to regulate reactor power. For lunar applications, designers favor passive control systems that automatically adjust reactor power in response to temperature changes, reducing reliance on complex mechanical systems that might fail in the harsh lunar environment. Thermoelectric converters represent the most robust technology for converting reactor heat into electricity. These solid-state devices rely on the thermoelectric effect, where temperature differences across certain materials generate electrical current. While less efficient than steam turbines used in terrestrial plants, thermoelectric converters have no moving parts and can operate reliably for decades without maintenance. Silicon-germanium thermoelectric elements have demonstrated efficiency, levels approaching 15% in space applications, meaning that a reactor generating 100 kilowatts of thermal power could produce 15 kilowatts of electricity. Advanced thermoelectric materials under development promise efficiencies exceeding 20%, making compact nuclear reactors increasingly attractive for space applications. Modular design philosophy drives every aspect of lunar reactor development. The entire reactor system must fit within the payload constraints of current launch vehicles, with individual components sized for robotic assembly on the lunar surface. The reactor core, cooling system, power conversion equipment, and radiative cooling panels are designed as separate modules that can be individually transported and assembled. Shielding presents unique challenges for space-deployed reactors. While the reactor must be adequately shielded to protect nearby equipment and personnel, excessive shielding adds mass and complexity to the design. Shadow shields, which protect only in specific directions rather than providing omnidirectional shielding, offer significant mass savings. A lunar reactor might employ a tungsten or depleted uranium shadow shield positioned between the reactor core and inhabited areas of a lunar base. Autonomous operation capabilities are essential given communication delays between Earth and Moon averaging 1 3/10 seconds each way. The reactor control system must handle routine operations, respond to emergencies, and conduct maintenance procedures without real-time human intervention. Artificial intelligence systems integrated into reactor controls could learn operational patterns and optimize performance over extended periods. The challenge of transporting a nuclear reactor to the Moon represents one of the most complex logistics problems ever attempted. Current heavy-lift launch vehicles like NASA's Space Launch System can deliver approximately 27 tons to trans-lunar injection trajectory, but even compact reactor designs approach or exceed these payload limits when accounting for necessary shielding, cooling systems, and structural components. SpaceX's Starship, currently under development, promises significantly higher payload capacity with a theoretical 100 to 150 tons to low Earth orbit and 50 tons to lunar surface. However, these capabilities remain unproven, and nuclear reactor components present unique transportation challenges beyond simple mass constraints. Reactor fuel assemblies require specialized containers to prevent criticality during launch and transport, adding substantial mass and volume to the payload. The most promising approach involves modular reactor designs that can be disassembled into components small enough for individual launches. The reactor core, containing enriched uranium fuel, would likely require its own dedicated launch due to nuclear safety regulations and specialized handling requirements. International Atomic Energy Agency guidelines for transporting nuclear materials impose strict limits on fissile material quantities per shipment, potentially requiring multiple launches just for the reactor fuel. Pre-positioning strategies could reduce transportation requirements by utilizing lunar resources wherever possible. The Moon contains significant deposits of aluminum, titanium, and other materials suitable for reactor construction. While uranium has not been definitively identified, in lunar samples, thorium deposits exist and could potentially support alternative reactor designs. Advanced manufacturing techniques, including three-dimensional printing and automated assembly systems, could fabricate reactor components from lunar materials. Fuel considerations dominate transportation planning. A 10-kilowatt reactor operating for 10 years would consume approximately 50 kilograms of highly enriched uranium, accounting for burnup and neutron absorption in control materials. This fuel mass, while relatively small, requires specialized transportation containers that could weigh several tons. The containers must maintain subcritical geometry throughout launch, prevent water intrusion that could moderate neutrons and increase reactivity, and withstand potential launch vehicle failures. Alternative fuel forms offer potential advantages for space transportation. Tri-structural isotropic fuel, originally developed for high-temperature gas reactors, encapsulates uranium in multiple layers of carbon and silicon carbide. These fuel particles are extremely robust, capable of retaining fission products even at high temperatures, and could eliminate the need for separate fuel cladding systems. The compact, durable nature of this fuel form makes it particularly attractive for space applications. Launch timing becomes critical when transporting reactor components. The reactor core and control systems should arrive together to enable rapid assembly and minimize exposure time on the lunar surface. Cooling system components and radiative panels might be launched separately, as these systems are less sensitive to prolonged storage in the space environment. Robotic assembly systems present both opportunities and challenges for lunar reactor deployment. Current robotic technology can handle many assembly tasks, but nuclear reactor construction requires precision and reliability beyond most current systems. Advanced manipulation capabilities, including fine motor control and the ability to work in protective suits or radiation environments, are essential for reactor assembly operations. In-space assembly offers an alternative to surface-based construction. Reactor components could be assembled in lunar orbit, then landed as a complete system. This approach would allow for more complex assembly procedures using specialized equipment that doesn't need to survive lunar landing. However, it requires additional transportation for assembly equipment and extends the overall mission timeline. Redundancy. Planning becomes crucial given the enormous cost and complexity of lunar transportation. Critical reactor components should have backup systems or replacement parts pre-positioned on the lunar surface. The isolation of lunar operations means that component failures could disable the reactor for years, while replacement parts are manufactured and transported from Earth. International cooperation could significantly reduce transportation costs and risks. Combining reactor components with other lunar payloads, sharing launch costs among multiple space agencies, and coordinating transportation schedules could make lunar nuclear power economically viable. The European Space Agency, Japan Aerospace Exploration Agency, and other organizations have expressed interest in lunar nuclear power development, creating opportunities for cost-sharing arrangements. Supply chain considerations extend beyond initial reactor deployment. Ongoing operations require spare parts, maintenance equipment, and eventual fuel replacement. Establishing lunar manufacturing capabilities for common reactor components could reduce long-term transportation requirements and improve operational reliability. Converting nuclear heat into usable electrical power on the Moon requires fundamentally different approaches than terrestrial nuclear plants. The absence of water eliminates steam turbine systems that generate over 80% of Earth's nuclear electricity. Instead, lunar reactors must rely on direct conversion technologies that can operate reliably in vacuum conditions for extended periods without maintenance. Thermoelectric conversion emerges as the most mature technology for lunar nuclear power systems. Thermoelectric generators utilize the Seebeck effect, where temperature differences across certain materials generate electrical current. Silicon-germanium alloys, proven in decades of space missions, can convert reactor heat directly into electricity, with efficiencies approaching 15%. While lower than the 35% efficiency typical of terrestrial nuclear plants, thermoelectric systems offer unmatched reliability and longevity. Advanced thermoelectric materials under development promise significant efficiency improvements. Scooter-Udit compounds, complex crystalline structures containing rare earth elements, demonstrate thermoelectric efficiencies exceeding 20% in laboratory conditions. These materials could nearly double the electrical output of lunar reactors, making compact nuclear systems increasingly competitive with alternative power sources. Thermophotovoltaic conversion represents another promising direct conversion technology. In these systems, reactor heat generates infrared radiation that specialized photovoltaic cells convert directly into electricity. Thermophotovoltaic cells optimized for infrared wavelengths can achieve efficiencies approaching 30%, rivaling terrestrial power plant performance. However, these systems require precise temperature control and sophisticated heat management to prevent cell degradation. Power distribution across a lunar base presents unique engineering challenges. Traditional electrical cables must withstand temperature swings of 300 degrees Celsius between lunar day and night. Copper conductors, standard for terrestrial applications, become brittle at extreme cold temperatures and may fail under repeated thermal cycling. Aluminum conductors offer better thermal expansion characteristics, but require larger cross-sections to carry equivalent current. Superconducting power transmission could revolutionize lunar electrical distribution. High-temperature superconductors maintain zero electrical resistance at temperatures achievable with cryogenic cooling systems. During the lunar night, natural cooling might maintain superconducting temperatures, enabling virtually lossless power transmission across large distances. However, maintaining superconducting temperatures during the hot lunar day requires active cooling systems that consume significant power. Power storage becomes critical for maintaining base operations during reactor maintenance or emergency shutdowns. Lithium-ion batteries, proven in space applications, can store substantial energy but suffer performance degradation at extreme temperatures. Battery thermal management systems must maintain optimal operating temperatures throughout lunar day-night cycles requiring sophisticated heating and cooling systems. Flywheel energy storage offers an alternative to chemical batteries. These systems store energy in rotating masses, maintaining power output through mechanical inertia. Flywheels can operate across wide temperature ranges and provide decades of service without degradation. However, they require sophisticated magnetic bearing systems to operate in vacuum conditions and must be carefully designed to prevent catastrophic failure. Fuel cell systems could provide backup power during reactor outages. Hydrogen-oxygen fuel cells generate electricity through chemical reactions, producing only water vapor as a byproduct. Stored hydrogen and oxygen could provide several days of emergency power, sufficient time to restart the reactor or implement alternative power sources. However, long-term storage of cryogenic hydrogen presents significant technical challenges. Load management becomes increasingly important with limited power generation capacity. A 10-kilowatt reactor must carefully allocate power between life support systems, scientific equipment, communication systems, and industrial processes. Automated load management systems could prioritize critical functions during power shortages and optimize energy usage based on operational requirements. Power quality considerations differ significantly from terrestrial applications. Electronic equipment designed for Earth-stable power grid may not tolerate the fluctuations inherent in small-scale nuclear power systems. Power conditioning equipment, including voltage regulators and harmonic filters, ensures stable electrical supply for sensitive electronics and scientific instruments. Integration with solar power systems could provide redundancy and supplemental capacity. During the 14-day lunar day, solar panels could reduce reactor load and provide backup power for critical systems. However, the lunar night eliminates solar power completely, making nuclear reactors essential for continuous base operations. Hybrid systems combining nuclear and solar power require sophisticated control systems to manage multiple power sources effectively. Electrical safety protocols must account for the unique hazards of the lunar environment. Traditional ground fault protection systems may not function properly in vacuum conditions, requiring alternative safety approaches. Personnel protection equipment must function reliably in spacesuits while providing adequate protection from electrical hazards. Grid expansion capabilities are essential for supporting growing lunar operations. The initial reactor installation should include provisions for connecting additional power sources and expanding distribution networks. Standardized electrical interfaces and modular distribution equipment enable systematic base expansion without requiring complete system redesign. Nuclear safety in the lunar environment presents unprecedented challenges that extend far beyond terrestrial reactor safety protocols. The Outer Space Treaty of 1967, which governs international space activities, requires that space operations be conducted in the interest of all mankind and prohibits the placement of weapons of mass destruction in space. While nuclear reactors clearly serve peaceful purposes, their potential for catastrophic failure raises complex legal and safety questions. The International Atomic Energy Agency has begun developing guidelines for space nuclear systems, but comprehensive. Regulations remain years away. Current draft standards emphasize multiple containment barriers, passive safety systems that function without external power or human intervention, and comprehensive environmental impact assessments. These emerging standards will likely require extensive ground testing and regulatory approval before any lunar reactor deployment. Reactor containment systems must address unique failure modes impossible on Earth. A breach in the primary containment could release radioactive materials directly into the vacuum of space, potentially contaminating large areas of the lunar surface with long-lived isotopes. Unlike terrestrial accidents where atmospheric dispersion dilutes contamination, lunar contamination would remain concentrated and hazardous for decades or centuries. Passive safety systems become even more critical in the lunar environment where human intervention may be impossible for extended periods. Advanced reactor designs incorporate inherent safety features that automatically shut down the reactor during abnormal conditions. Temperature-sensitive control rod systems use thermal expansion to insert neutron-absorbing materials when reactor temperatures exceed safe limits, providing automatic shutdown capability without external power or human action. Emergency response planning must account for the extreme isolation of lunar operations. Earth-based emergency response teams cannot reach the moon for days or weeks, even under optimal conditions. Lunar reactor operators must be thoroughly trained to handle any conceivable emergency situation independently. Automated systems must be capable of placing the reactor in safe shutdown mode without human intervention during communication blackouts or crew incapacitation. Radiation protection protocols require fundamental modification for lunar operations. Earth's atmosphere and magnetic field provide natural radiation shielding that doesn't exist on the Moon. Background radiation levels on the lunar surface already exceed acceptable limits for extended human exposure, complicating radiation safety. Calculations. Reactor shielding must account for the existing high radiation environment while providing adequate protection for personnel and equipment. Nuclear material security presents unique challenges in the international lunar environment. Traditional physical security measures rely on controlled access and armed guards, neither practical for lunar operations. Instead, security systems must focus on monitoring and tracking nuclear materials, with automated systems detecting unauthorized access or material diversion. Advanced authentication systems and tamper-evident technologies become essential for maintaining nuclear security. Waste management strategies must address the long-term storage of radioactive materials on the Moon. Spent nuclear fuel remains hazardous for thousands of years, requiring secure storage systems that can withstand micrometeorite impacts, temperature cycling, and potential seismic activity from meteorite strikes. Deep geological disposal, the preferred approach on Earth, may not be feasible on the Moon due to limited knowledge of lunar subsurface geology. International coordination becomes crucial for managing nuclear risks that could affect multiple nations. Lunar operations. A reactor accident could contaminate shared resources like polar ice deposits or interfere with scientific research conducted by other countries. International protocols must establish liability frameworks, emergency response coordination, and environmental restoration responsibilities. Risk assessment methodologies developed for terrestrial reactors require significant modification for lunar applications. Traditional probabilistic risk assessment considers external events like earthquakes, floods, and human error. Lunar risk assessment must address micrometeorite impacts, solar particle events, equipment failures without possibility of repair, and the unique psychological stresses of isolated operations. Quality assurance programs must ensure that reactor components can function reliably for decades without maintenance or replacement. Traditional nuclear quality assurance involves extensive testing and inspection programs supported by large industrial infrastructures. Lunar reactor components must meet even higher reliability standards, since replacement or repair may be impossible for extended periods. Environmental impact assessment for lunar nuclear operations requires developing entirely new analytical frameworks. While the Moon lacks a biosphere to protect, reactor operations could affect future scientific research, resource utilization, and human activities. Radioactive contamination could interfere with astronomical observations, geological research, or future industrial development. Insurance and liability considerations present complex challenges for lunar nuclear operations. Traditional nuclear insurance pools may not cover space operations, and existing space insurance typically excludes nuclear risks. New insurance frameworks must address the unique risks of lunar nuclear operations while providing adequate coverage for potentially catastrophic accidents. Decommissioning planning must begin before reactor construction as end-of-life reactor. Management presents even greater challenges than initial deployment. Removing spent fuel and contaminated components from the Moon may be prohibitively expensive, requiring in-place decommissioning strategies that safely isolate radioactive materials for extended periods. The successful deployment of nuclear reactors on the Moon would fundamentally transform humanity's relationship with space, opening possibilities that remain pure science fiction today. A reliable source of continuous power would enable permanent lunar settlements capable of supporting hundreds or thousands of residents, transforming the Moon from a destination for brief scientific missions into humanity's first extraterrestrial colony. Industrial applications of lunar nuclear power could Revolutionize space exploration economics. Aluminum smelting, powered by nuclear reactors, could produce structural materials directly on the Moon, using local ore deposits. The Moon's low gravity makes it an ideal launching point for deep space missions, and locally produced materials could reduce launch costs by orders of magnitude. A kilogram of aluminum produced on the Moon costs far less to deliver to Mars than the same kilogram launched from Earth's deep gravity well. Lunar manufacturing capabilities powered by nuclear reactors could produce spacecraft, habitats and equipment for exploration throughout the solar system. Three-dimensional printing technologies, powered by abundant nuclear electricity, could fabricate complex components from lunar materials. Advanced manufacturing might even produce electronic components and scientific instruments, reducing dependence on Earth-based supply chains for space exploration. The Moon's potential as a refueling station for deep space missions becomes compelling with nuclear-powered fuel production. Electrolysis of lunar water ice, discovered in permanently shadowed polar craters, could produce hydrogen and oxygen propellants. Nuclear reactors provide the enormous electrical power required for large-scale propellant production, enabling regular cargo and crew flights throughout the inner solar system. Scientific research capabilities would expand dramatically with reliable nuclear power. Radio astronomy observations, freed from Earth's radio interference, could reveal cosmic phenomena invisible from our home planet. The Moon's far side offers a uniquely radio-quiet environment for detecting signals from the early universe or searching for extraterrestrial intelligence. Nuclear-powered research stations could operate continuously, collecting data through the long lunar night when solar power is unavailable. Asteroid mining operations, perhaps the most economically transformative space industry, require enormous amounts of power for ore processing and material refinement. Nuclear reactors could power mining equipment, smelting facilities, and spacecraft. Manufacturing operations in the asteroid belt. A single metallic asteroid contains more platinum than has ever been mined on Earth, potentially worth trillions of dollars and revolutionizing terrestrial electronics and manufacturing. Mars exploration would benefit enormously from lunar nuclear power development. Technologies proven on the Moon could be adapted for the red planet, where dust storms and seasonal variations limit solar power effectiveness. Nuclear reactors could support large-scale Mars settlements, terraforming experiments and industrial development necessary for eventual human colonization. The economic implications of successful lunar nuclear power extend far beyond space exploration. Helium-3, a rare isotope potentially useful for advanced fusion reactors, exists in lunar soil deposited by solar wind over billions of years. While fusion power remains technically challenging, nuclear-powered mining operations could extract helium-3 for transport to Earth, potentially providing clean energy for centuries. Space-based solar power becomes feasible with nuclear-powered construction capabilities. Massive solar panel arrays assembled in space using lunar materials could beam clean energy to Earth via microwave transmission. These systems could generate terawatts of power without terrestrial environmental impact, addressing climate change while providing abundant clean energy for global development. Advanced propulsion systems enabled by nuclear power could reduce travel times throughout the solar system. Nuclear electric propulsion, powered by lunar reactors, could accelerate spacecraft to unprecedented velocities. Journey times to Mars could be reduced from 9 months to 3 months, and outer planet missions that currently take decades could be completed in years. The psychological and cultural implications of successful lunar nuclear colonization are profound. Permanent human presence beyond Earth would fundamentally alter humanity's perspective on our place in the universe. Children born on the Moon would be the first generation of truly spacefaring humans, adapted to life in reduced gravity and artificial environments. International cooperation frameworks developed for lunar nuclear power could serve as models for future space governance. Successful management of nuclear technology in the international lunar environment would demonstrate humanity's ability to cooperate on the most advanced and potentially dangerous technologies. These precedents could guide governance frameworks for asteroid mining, Mars colonization, and eventual interstellar exploration. The timeline for these transformative developments depends heavily on political will and economic investment. Conservative. Estimates suggest that initial lunar nuclear reactors could be operational within 15 to 20 years, with industrial applications following within decades. However, accelerated development programs with substantial international cooperation could achieve these goals much sooner. Ultimately, nuclear power on the Moon represents more than just an energy source. It embodies humanity's determination to become a truly spacefaring civilization. The same physics that Enrico Fermi unleashed in that Chicago basement could power our expansion throughout the solar system, ensuring that the human story continues far beyond our home planet. The Moon, long a symbol of dreams and aspirations, could become the foundation for humanity's greatest adventure among the stars.